a sequence is what we're looking at, a sequence. And what is a sequence? It's any well-ordered list of numbers, McFall. A sequence is any well-ordered list of numbers, and this is how we're going to denote it. A1, comma, A2, comma, A3. All A1 represents is the first number, and then A2 is the second number. We are only going to look at infinite sequences. It is, excuse me, yes, it is an infinite. It is infinite because you have the dot, dot, dot. If it ended at A sub n, that would mean a finite sequence. We are only looking at infinite sequences. That's it. So you're going to see things that potentially look like this. These are both three ways of saying the same thing, or two ways of saying the same thing, or three ways of saying the exact same thing. So this is the set of all numbers starting with n equals 1 going towards infinity, where each term is defined as n over n plus 1. Another way to say it is a sub n is equal to this, or you could just do the look. You could just list it out. This is the nth term, and why do we have the dot, dot, dot afterwards? Because we're specifically looking for an infinite sequence here. What about this one? What's that negative 1 to the n going to do? And n is going from 1 to infinity, and n is always 1. Whole numbers. You're not doing fractions. Things get real weird if you do fractions, I guess. What's the negative 1 to the n going to do this overall? It alternates sign, right? It goes back and forth. And then you have n plus 1 over 3 to the n. Or you could write it as a sub n. Or you could write out the actual thing right here. Or you could add the actual thing. Okay. Visually. What this means is, let's say we had the n values are progressively getting bigger that way. Okay? And we're saying that the output values will say, I don't know, the an value, the output on the y-axis here. So let's say we had a sequence where it went like this. And it kept on getting really close right here. And meaning, visually speaking, it looks like a sub n is getting really, really close to L. The key thing to look at here, and this is something we don't get too much in depth with, because we do not do epsilon delta proofs in AP calculus. You're welcome. He just shuddered, which is a good reaction. What's the key thing? As close as we like. As close as we like, right here, by taking n to be sufficiently large. What this says is, we can say that an goes to L as n goes to infinity if every time you specify a distance on the y distance, we can get that close to L by taking n to be sufficiently large. Another way to say it is, you can always get closer to L. You can always get closer to L. So if you can always get closer to L, past anything. So you could say, get within 1/1,000,000th. And I'll say, okay, well then you got to take n to be a trillion. Then you can say, get even closer. And I say, okay, take it to 1,000,000,000. As long as you can get close enough, as long as, and as it says right here, as close to L as we like by taking n sufficiently large, we say that L is the limit. Does that make sense a little bit, everybody? Now here's the thing. Yeah, 0 is not going to be a distance, exactly. But here's the thing. Saying that out loud and proving it is entirely different. Up and down, you have epsilon delta proofs. Epsilon will be side to side, as far as I remember, and delta is up and down. Is that right? Do I remember that correctly? Epsilon delta proofs. Yeah. The two symbols you're going to see are this. The two symbols you're going to see are epsilon delta. This is epsilon, and this is delta. You will do a ton. If you study math in college, you will do tons of epsilon delta proofs. They are what you use primarily in many places to prove what you are learning in AP calculus. Things that you didn't realize need proofs. But this phrase right here, as close as you like, let me notarize that even better. As close as you like, that is essentially them saying epsilon delta proofs. They list them out in this book. You can read about them. They are not covered at all in the AP test, and it takes a long time for them to make sense. So we do not cover them. Maybe after we take the AP test, that'll be one thing we can discuss. It's really cool, and I think it'll help you a great deal in college. Because by the time you see the really scary epsilon delta proofs, you say, okay, kind of get this already. Or you'll know enough to run away, like run screaming from the room. Epsilon, so what you're looking at is you're looking to get, as long as, so if this right here, this distance right here, that's going to be epsilon right there. So for every epsilon that you specify, I can say the delta is going to be on the x-axis, the x-axis. So I have to get within this close on the L, I have to get within this close on the x-axis, delta. So delta equals x values. Okay, let's keep moving. If I can get this back, there we go. That you need to remember. They're not super earth-shattering, and they're essentially the same ones you've already known about. But you just need to remember these right here. You need to remember if they're both convergent. If you do the limit of the sum, you can do the sum of the limits. The limit of the subtraction is the subtraction of the limits. What can you do with a constant? You can factor it out. If they're both convergent, you can take the product and do it separately. If you have a division, you can do the numerator and the denominator separately. If you have the power, what can you do with the power? Bring it out. As long as an and bn are what? They better be convergent. If they're not convergent, these things generally tend to break. The way, if you wanted to do this, is to divide everything by n. If you divide everything by n, you end up with the limit as n goes to infinity of 1 over 1 plus 1 over n, which is the limit. I'm just writing this out like you generally won't over the limit as n goes to infinity of 1 plus 1 over n. So that's going to be 1 over the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 1 over n. So that's going to be 1 over 1 plus 0 is 1. So that's the technical way you would write it out, the technical way. But do you generally have to break it down that far? No, you do not. Value goes to 0, then the limit of the function itself goes to 0. Exactly. So all you're doing is you can think of it as you're flipping that sign over. And if you flip it to the positive everywhere, you just have the limit as n goes to infinity of 1 over n. And what do we know that is? 0. That's where the backing comes from. You can use logic, but this is the theorem that gives you that ability. So what does this say? Discuss the convergence of the sequence n factorial over n to the n. Exactly. Who goes to? It is a race, but it's not totally clear, right? I mean, you could think in your head, which one do you think is bigger, n factorial over n to the n? Those are both hugely explosively growing functions, right? Which one do you think is growing faster? Okay, think of it in terms of what happens if n was 10? What's n factorial? 10 times 9 times 8 times 7 times 6, right? But what's 10 to the 10th? It's bigger, right? So which one do you think is bigger? Okay, so it's definitely not going to go to infinity. So at this point, we think it's either going to converge. We think it's either going to converge to 0 or some static number. Right? To converge, it has to converge to a static number. Okay, can't you what? But how do you prove that?
Okay, so let's say we use 10. 10 factorial is 10 times 9 times whatever.
Yeah.
And n is 10 times whatever.
Yeah.
So you get
Oh, okay. So what does this look like? Hold on. I like what you're saying. So you're saying, let's just do it out here. So a to n equals n factorial over n to the n. So that's going to be n times n minus 1 times n minus 2 all the way down, right? Over n times n times n times n, right? So it definitely looks like the bottom is going to be bigger. So let's say we did a10, for example. It's going to be 10 factorial over 10 to the 10th. So you said 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then it's just 10 times 10, 10 times. Okay, so what'd you say about that? Kill a 10? Okay, I like that, okay. Okay, so now we have, okay, I like this idea. You have, okay. So, n, this is what you're saying, I think. N equals n minus 1 factorial over n to the n minus 1. Okay, I like this idea. This did something, right? This did something. It also seems like did it really help? I mean, it gave us something. It made it 10 times smaller, or n times smaller. You're like, yay, 10 times smaller. But then you still realize you're stuck in like trillions land. Let's try something. I'm not going to do anything other than change the order. This is equal to 1 times 2 times 3 times 4, all the way up to what? N, right? And this is n times n times n times n, right?
Yeah.
So what do you have? You have 1 over n times what? 2 times 3 times 4 all the way to n all over this is n to the n minus 1, right? Do you agree with that? Hold on. Oh, okay. So there's you just noticed, you now know that this, yes, your n is going to, and that's not infinity, that's some weird symbol. So what is this going to? 0. But what about this?
Well, you can do that.
What do you mean it doesn't? We have to be careful. What do you mean it doesn't matter?
Well, all of them are also
Hold on.
Now you can do your properties of limits and like
Okay, so that one's going to 0. So we also have what? 1 over n times what? 2 over n times 3 over n all the way to n over n, right? So all of these, what is this one going to? 0. What's this one going to? 0. What's this one going to? 0. This one's going to 1, but this one is what? N minus 1 over n? Does it go to 0? Oh, be careful. What does n minus 1 over n go to? It goes to what? 1. What? Whoa. Can it, but here, we have a lot of things that are multiplying together to get 0, 0, 0, or what? 1. So what do we think this is going to go to? So it's all zeros and one. Do we think it's all zeros and ones? So what do we think this is going to? Great. Let's just try it here. Let's try this. We're looking at, let's say it was 2 times 3 times 4 times 5 all the way to what? All over n to the what? Agreed? We know that has to be less than or equal to what? Can't be any greater than 1, right? Do you agree it can't be any greater than that? And we also know it has to be greater than what? Must be agreed to say greater than, that's fine. Do you agree with that? Okay, so now we multiply everything by 1 over n. So we have 0. Yeah, so 0 less than or equal to exactly what we wanted, which was n factorial over what? N to the n is less than or equal to 1 over n. So the limit as n goes to infinity of 0 is what? 0. And what's the limit as n goes to infinity of 1 over n? 0. Therefore, by squeeze theorem, the limit as n goes to infinity of n factorial over n to the n is equal to 0. It's kind of cool. When you see increasing, this definitely will come up as a problem at some point because of my this inconsistency and how I learned it personally. When you see this, think of it as strictly increasing. Strictly increasing. Yes. Increasing and decreasing, exactly.